So in this video we will be writing code to solve the time varying temperature profile of the bar from part 2, but this time we will be using implicit differencing or the Crank-Nicolson method instead of our explicit differencing that we used in part 2. So as you can see, I already have the start of explicit differencing up here, and how this is going to change with Crank-Nicolson's method is this second derivative of temperature and position. We are actually going to be taking into account the temperatures at the next time step, and what it's going to end up being is an average between those temperatures at the previous time step and the next time step. So what that will end up being is we'll have T J plus 1 N plus 2 T J comma N plus T J minus 1 comma N, and then all that over delta x squared, and then plus those same things, but at the next time step, n plus 1. So again, it'll just be all the same, but instead of n, it'll be n plus 1. And then this will be over 2 as well. So now what we're going to want to do is get all these n plus 1, sub n plus 1s on the same side, and all these n values on the same side. But first, what you can notice that we can do is we multiply this delta t over to this side and take out these delta x's on both of these, where we will end up with our thermal diffusivity times delta t over delta x squared times 2. And as you can see, that just equals our r value from the other videos over 2. And we're going to end up just calling that u for once we get coding with all these values. So that means we can erase these parts. Erase all these, erase this, and just put a U here. So now it'll be a lot more simple when we're trying to get all those n plus 1s and n on their own side. So I did notice that I did mess this up originally. These should be subtraction signs. Subtraction and subtraction like that. And then now we can get the n's and n plus 1 on their own side. So to start off, we'll have negative u t j plus 1 n plus 1 plus 2u plus 1 t j n plus 1 minus u t j minus 1 n plus 1. And then now we can do the other side with our n's, and that one will start off with it'll just be u t j plus 1 n plus 2u minus 1 t j comma n and then minus u c j minus 1 n. Like that. So this should be plus, actually. And then this should be 1 minus 2u. And I can just change this to match that as well. 1 plus 2u. And now that should be correct. Yeah. So now we are going to use matrix multiplication to describe our equation that we just found. So we're going to start off by writing out the vector of unknown internal temperature values at the later time step. So obviously the first one is going to be 1 time step to the right of our left boundary, which we're just going to call T1. And then our last temperature value down here is going to be 1 time step to the left of our right hand side boundary, so we're going to call that T n minus 1. N minus 1. And then again, we'll have all those temperatures in between, T2, T3, and so on, all the way there. So now if we start with T sub 2, and we're plugging in up here into our left-hand side, since we're trying to get this left-hand side vector represented. If we plug that in into here, we would end up getting 2 minus 1, which would be T sub 1. So we got that negative u times our T sub 1 over here. So we put it on the far left over here, negative u. And then that means when we plug this in here, T sub 2, we want this 1 plus 2u to end up multiplying by here. So we put that here, 1 plus 2u. And then finally the same thing over here, and we have negative u. Now if we go for T1 up here, we plug in that T1 up here, we get T sub 0, we'll end up having negative u here for this, and then the T sub 1 here, and we'll have the 1 plus 2u here. As you can see, if we plug that T sub 1 there, the 1 plus 2u is multiplied by that. And then we can just keep going with this, and you will end up seeing a pattern where if we do T sub 3 here, plugged in up there, actually this should be here, because again we want it multiplied by that T sub 1 plus 2u. And then now, so if we do T sub 3 in there, we want to multiply, we want this negative u times T sub 2, so we put it there, and we have 1 plus 2u here. And then if we're going to T sub 4, we'd have a negative u right here as well. So I can see we get this little pattern here, which we can end up solving in Python later, but this is just a good representation of our left-hand side equation. So now we can start working on the right-hand side over here in this vector. So first, we're going to do it for this T2. So if we plug in that T2 there, again, these are just going to be all known values. We don't really have to care about order, since it's all just known values. If we plug that T2 in there, we'll just end up with u T3, and then plus 1 minus 2u T2 plus U T3. And then if we just keep going down here for T3, then it's just all going to be increased by 1. And you see here U T4 instead of T3. And so on. This would be T3 instead of T2. And then here T2. Now if we just kept going, all these, or just keep following that pattern. Wait a second. That should be T1. I thought something here looked kind of wrong. Yeah, so just keep following this pattern, increasing these by 1. If we get to T4, then all these would just be increased by 1. But this T1 and Tn minus 1 are actually going to look a little bit different. So we will move on to those next. So if we were to write these for T1 and Tn minus 1 normally, we would end up with U T2 plus one minus 2U. Again, these should be minus as well. Did not notice that I messed that up in the last part. And then T1, and then plus U T0. And then down here, it would end up being T U Tn. I'm gonna give myself some more space here. U Tn plus 1 minus 2U Tn minus 1 plus U T sub n minus 2. Now what will change about these is that, as you notice, we have a T sub 0 here and T sub n here, and those two values are our left and right bounds in our problem. T sub 0 being the left bound, T sub n being the right bound, and as you know, we know those values. So what we can do is we're going to end up adding this U and this U and this U and this U, and it'll end up being 2 U T sub 0 and 2 U T sub n in our final equation. So now this matrix multiplication is completed, and we will be coding out this triangle matrix in Python and solving it and plotting in the next part of this video. So now we're going to start the plotting portion of this video. So as you can see here, I have copy and pasted what we had in part 2 of this video in the coding. I've changed a little bit. I've put in a title and then some axis title as well, and then I changed it to Plotly Dark. This would just make the graph look a lot nicer. I also added these T equals on here, so our legend over here is more nice. And then one other thing that we are going to have to do is we're going to have to change this R value to U, which we had on our board. And then that means that this whole thing is divided by 2. So let me run that, and that should be good. So let's define our first matrix A. And we're going to use numpy zeros. And we're going to have 3 diagonals. So that means our first value will be 3. And then for our length, we're going to want however many position increment we have in our bar, which again is our n value of 20. So we're actually going to want to n minus 2 though, because we want to account for those two temperatures that we already know at the left and right bound are 50 and 80. So that will be our first matrix. And then now we can look at how we're going to index these non-zero values in our matrices. So the first one, obviously, if we look at our thing here, negative u, and then 1 plus 2 times u, and then negative u. So we're going to type each of those out. Negative u, 1 plus 2 times u, and then negative u again. And then obviously our first one is going to start in the first row. And then the second one in the second row. And again, Python indexing starts at 0, so this is really first, second. And then here, the third. So now for the columns, we're going to have to perform slicing. And if we look at our matrix here, you can tell that for this first row, or for this first diagonal, we don't have anything in the first column. So that's why we need to perform the slicing. So what it's going to be is just a colon and then a 1. Or it should be a 1 and then a colon since we are excluding that first column. And then now for the second diagonal, it's going to be there for all the columns, so we can just denote that by a colon. And then finally for the last diagonal, negative u, as you can see we don't have it in the last column. So we can denote that by a colon and then a negative 1. Again, that negative 1 is denoting that last column, but for slicing notation, it actually is not included in our slicing. So now what we want to do is we're going to want to put in our for loop here our matrix here with our right hand side of the equation. So how we're going to do that again is by indexing using these temperatures from 2 to n, 1 to n minus 1, and 0 to n minus 2. So we're just going to start off with the u times t, and this is going to be 2 colon, and then plus, it's going to be 1 minus 2 times u, 1 minus 2 times u, and then t, and this will be from 1 to negative 1, and this should be times here, plus u times t, and this one will be 0 to negative 2. So I did notice I'm going to put parentheses around all this just to make sure that it doesn't mess up. So it knows that we're adding these whole things together. And then we can get rid of this, that is from the last part. And then now what we have to account for are these 2u, tn, and 2u, 20. So how we're going to account for that is we're just going to put those in ourselves. So B0 is going to be equal to B0, oh, not O, 0 plus then our U times T0 and then we can just copy this and change it all to -1 for that last value. So now finally we can use that Python solver that I kind of mentioned in the last video for these matrices. It's from SciPy linear algebra and it's called solve_banded. So I'm going to type that in here and that's going to end up giving us our temperatures. From 1 to -1. So again, it's solve_banded right here. And it's going to tell us to put in this L and U, which in our case is 1 and 1. And then we just need to put in our two matrices A and B. And then I'm also going to change our range. I'm going to make it like 500 and make this 25. And also I'm going to make our starting 25. And then we need to make our time step greater than 0.5. So let's make it like 1. And let's run all and see what type of plot we get. So we get this nice little temperature profile plot from our Crank-Nicolson method.